Hello class, welcome to the next segment in lecture 27, and in this segment we're going to take a look at how our vertical velocity component in our wind vector changes when we go from height coordinates to pressure coordinates, or standard Cartesian coordinates to a pressure coordinate system. So that's what we're going to be covering in this segment, and to start things off, I'll sort of refresh your memory on what one definition of the vertical component of the wind speed actually is. And also, I'll just throw this in as sort of a side note. When we go towards pressure coordinates, our x and y axes are still the same. So our x direction still our positive x direction still points to the east, and our positive y direction still points to the north, whether we're in Cartesian coordinates or pressure coordinates. The only change happens in the vertical direction. So in the vertical component of the Cartesian grid, that's height above ground level, whereas in pressure coordinates, that's where the vertical coordinate is in fact replaced with pressure. So the x and y coordinates are still the same in both Cartesian and pressure coordinates. The difference is in the vertical component. So to refresh your memory, Cartesian coordinates, the vertical wind velocity or wind speed is defined as the change in height over the change in time, change in vertical coordinate displacement, change in vertical displacement times the change in time. And of course, the units for this, typically height is represented in either meters or kilometers, but usually when you're representing some sort of speed using MK as units, the units for that are going to be meters per second. And again, just to sort of get our bearings, straight. So again, this is the same diagram that we introduced at the end of the first segment. So again, by the way that we define this kind of goes back to what we introduced in lecture 1. We define a positive value of W as the vertical component of the wind. A positive value of W represents a wind that's traveling directly upward. So something like this. So as time progresses, the thing in question, whether that's an air parcel or whatever that might be, as time progresses, as time goes forward, the z coordinate increases. So that's kind of where this definition comes from. As we go towards higher values of z as time goes on. So dt is always going to be positive, and if our change in z is also positive, then that means that we've got a positive value of w, which represents a rising parcel of air or some sort of rising motion. And if we look at the flip side of that, if we look at a case where our value of z decreases with time, so as time progresses we go towards lower values of z, that would correspond to sinking motion, and that would also correspond to a value of w that is less than 0. So that's what we see in Cartesian coordinates. Now let's take a look at how things change when we go over to pressure coordinates. So to start things off, instead of using the regular Roman letter W, here we use the Greek letter omega to represent the vertical velocity and pressure coordinates. And something that I should note right away is this omega is not to be confused with the vorticity vector omega. So vorticity vector is, first of all, it's a vector quantity, but it's also represented using lowercase omega. This symbol omega represents the vertical velocity and pressure coordinates. So this is not to be confused with the vorticity vector that we defined in some earlier lectures. And this is defined if we're going from using the standard Cartesian grid coordinate z to using pressure as a vertical coordinates, instead of representing this in terms of a change in height above ground level, then our velocity will be represented as a change in pressure with respect to time. So if in the standard Cartesian case, we had some sort of length, meters or kilometers or whatever that might be, divided by some unit, some time value. So the units for this would be meters per second. If we got pressure in the numerator and time in the denominator, then the units for this will in fact be pascals per second. So that's one glaring change to notice right away is when we go into pressure coordinates, our vertical velocity is no longer in terms of meters per second, it is now in terms of pascals per second. And if we take a look at how this looks on some sort of plot, so again, pressure increases as we go downward, and that's in contrast to when the z-coordinate increases in the Cartesian grid. In pressure coordinates, the pressure increases as you go downward. Now let's take a look at the same arrow where we had rising motion in the Cartesian grid. So we still have rising motion here. But one thing that we should note is in the case of pressure coordinates, if we've got rising motion, as we progress through time, you can see we are in fact going towards lower pressures. If we're going towards higher elevations as time progresses, we've got rising motion. but going towards higher elevations means we're going towards lower values of pressure. So that means this term, this numerator dp will be negative, dt is still always positive. So that means that for rising motion, the vertical velocity and pressure coordinates omega will in fact be negative. So a positive value for w in Cartesian coordinates corresponds to a negative value for omega in pressure coordinates. And again, the reason why is because we've got rising motion, we've got an air parcel or something that's moving from higher pressure to lower pressure, meaning this term in the numerator is negative and dt is still positive. So that means our value for omega must be negative. So a negative value for omega indicates rising motion, and a positive value for w indicates rising motion as well. And then for sinking motion, where we have some sort of air parcel or something going from higher elevation to lower elevation, and again in the atmosphere, if we have something going from a higher elevation to a lower elevation, then we must be going from a lower pressure to a higher pressure. So if our air parcel is, the pressure of our air parcel is increasing with time, that means this term in the numerator is going to be positive and this denominator is still positive, then that would imply that omega is positive as well. So, and this is one of the things that can be confusing at first. If you have a standard Cartesian coordinate system, w is going to be positive for rising motion, omega is going to be negative for rising motion, and then again in the Cartesian, w will be negative for sinking motion, and the pressure coordinates, omega, will be positive for sinking motion. And the reason, and again, this can be kind of confusing, but the thing that you want to pay attention to is my pressure increasing or decreasing with time? And also a side note, these are in fact Lagrangian terms, and that'll be important in just a minute. But you want to focus on whether this numerator is increasing or decreasing to diagnose the sign of omega. If we have rising motion, that means our pressure is decreasing because we're going towards higher elevations where the pressure is lower. So our pressure is decreasing, hence omega is negative. And in the case of sinking motion, we're going from lower values of pressure to higher values of pressure, so our pressure is increasing, which corresponds to a positive value for omega. So it might be helpful to sort of rewatch this particular part just to make sure that you're not getting confused here. It also doesn't help that the symbols here also look really similar. The omega kind of looks like a W, but unfortunately that's the choice of symbols that has been used by the meteorology community. So unfortunately I have no control over that, and we're just going to have to live with it. But let's actually sort of extend this topic a little bit and talk about how we can relate the Cartesian vertical velocity to the vertical velocity and pressure coordinates. So there must be some sort of relationship here, because as one increases, the other decreases, and also vice versa. And that mathematical relationship is what we're going to look at now. So again, omega is defined as the Lagrangian derivative of pressure. And something that we've done a few times before is we can take this Lagrangian term and expand it into the local change in pressure, or the local change in some quantity, plus all the advection terms. And if we do that, we can expand this Lagrangian term, this Lagrangian derivative, into the Eulerian derivative, partial p, partial t, plus all the advection terms. And if you think about what we actually observe in the real atmosphere, so this would be the local change in pressure. So some sort of pressure change due to some sort of outside influence, which is usually very small if you're looking at, say, synoptic scale motions. And also if you're looking at the synoptic scale, if you think about the horizontal variation in pressure, usually that's going to be at most 10 or 20 millibars per about 1,000 kilometers. That's going to be pretty small. But when you think about the vertical variation in pressure, if you go up, say 1,000 kilometers, if you go up 1,000 kilometers, then you're going to be going towards much lower pressures. In fact, if you go up just 1 kilometer, your pressure is going to drop by 100 millibars. So usually, this term is going to heavily dominate over these other terms in this expansion here. So we can usually neglect these terms. They're usually small enough to be negligible. The pressure varies a lot more profoundly in the vertical direction than it does in the horizontal direction. So we can assume that these are negligible, and we can eliminate them from their equation, and we can approximate omega as being equal to the Cartesian vertical velocity w times dp dz. But this expression dp dz might also look familiar. In fact, this is in the hydrostatic equation, or the equation for hydrostatic balance. So we can simply take the expression for dp dz is equal to minus rho g, again where rho is density, g is acceleration due to gravity. And we just simply take this expression and substitute this in for dp dz to obtain the following relationship. So we get that our vertical velocity and pressure coordinates omega is equal to minus density times acceleration due to gravity times our vertical velocity and Cartesian coordinates w. And this mathematical relationship makes sense, right? Because as we saw in the previous slide, where we're taking a look at how omega and w are inversely related to each other. If you take a look at, say, an example where w is positive, then I'm going to be having a positive value multiplied by a positive value multiplied by a positive value multiplied by this negative sign. So if w is positive, that means omega is negative, which is consistent to what we saw earlier. And if we have a negative value of w, then we're going to end up with a positive value on the right-hand side of this equation, which will give us a positive value for omega, which again matches up with what we looked at earlier. So that's going to do it for this second segment on pressure coordinates. That's going to do it for a look at how the vertical wind changes in pressure coordinates. And in the next segment, we're going to take a look at how the mass continuity equation changes when we go into pressure coordinates. So with that, I will see you all in the next segment.